First law of thermodynamics. So let's assume we have a system which is isolated from the entire part of the surroundings. Okay, so there is this area, there is going to be no change in heat and no change in work because it's isolated. So automatically, there will be no change in the internal energy of this system. And from there is where we get the first law of thermodynamics. So the internal energy is not going to change of the system, which is isolated. Okay, so from that, we can easily say that when energy can neither be created nor destroyed, but it can be converted from one form to another. We've learned about this in various ways. Like we talk about when you're in the younger sections or younger younger years of your education, you'd be taught about how when you switch the switch on, you have the electrical energy getting converted to maybe light when it's a tube light. So all of this is already been there. Okay, it's just that now we are adding the word thermodynamics to it. So according to the first law of thermodynamics, energy can neither be created nor be destroyed, but it is converted from one form to another. And this is also applicable to chemical reactions as well. And that's why we're learning it in chemistry, obviously. So here in a chemical reaction, there can be an energy getting absorbed or energy is going to be released. There are only two possibilities. And that's because when there is an absorption of energy taking place, there's probably the formation, the breakage of bonds, the formation of new bonds, all of them are again related to energy only. Not only that, when energy is released, it means that the bond between the two atoms probably broke and there is a lot of energy that is getting released. Or it could be a weaker bond was formed and so there is a lot of energy that is being released. So this particular law can be it can be stated in other ways where you basically say the total energy of the universe remains constant. Or when you have an isolated system, there is going to be no change in energy, which is what we started with. So this particular law of thermodynamics, the first law, does not have a proper proof or anything, but theoretical proof. I can give you some examples where you can say that, okay, first law of thermodynamics is followed. Now, let's take, for example, a machine, which does, let's say, it's the simplest one, I think, is probably a light, right? Or I don't know if it's considered to be a machine in the technical sense. Okay, let's take, for example, a car. Okay, car, it's going to take fuel in, right? And what's going to happen is it's going to release some amount of energy because it's going to burn this fuel, and this burning of the fuel is in turn powering the car, and that in turn is making sure the work is being done. Now, if there was no fuel and if there was no heat, then there would be no transport for us to move with. Okay, that's like a very simple example. Another one was actually James Joule. What he did was he conducted a couple of experiments, or many experiments rather, and what he saw that for every 4.183 joules of work that was being done, there was an increase in temperature, or rather there was increase, or 1 calorie of heat was produced. And joule is the unit of work, calorie is the unit of heat. So 4.183, for every 4.183 joule of work being done on the system, there was 1 calorie of heat that was being produced. Another chemistry-based example, because this is for chemistry that we're learning. Let's take example of water. Okay, now this is actually a reversible reaction. Okay, so H2 plus O2, or I should not probably say reversible, but yeah, it requires some amount of heat. Now, what's interesting about this is that the amount of energy that is required by hydrogen and oxygen, or let me just balance this equation because it bothers me. Yeah. So the amount of energy that is required by this, the conversion of hydrogen and oxygen to form water, is approximately 286.4 kilojoules per mole. That's the amount of energy that's required. Now, surprisingly or interestingly, when the water molecule is broken, or when, if you want to talk about it even more specifically in terms of to make sure that we have the same number of molecules, I'm just going to put 1 by 2 O2. Okay, that basically balances out the equation. So when H2O breaks, it releases 286.4 kilojoules per mole. That is pretty good. So when hydrogen and oxygen convert to form water, you have 286.4 kilojoules per mole getting absorbed. Whereas when water is getting converted back to hydrogen and oxygen, you have 286.4 kilojoules per mole getting released. So these are a few examples of the first law of thermodynamics. Now, obviously, because it's thermodynamics and it's physical chemistry, we will be talking about the mathematical expression of the first law. Now, as we know, the internal energy can be changed in two ways, and they are, I'm going to pause for you to think about it, parallelly write about it. So heat and work. These are the two ways where we are going to have a change in internal energy. Right. So when you have heat getting basically heat getting added to the system or heat getting kicked out of the system. Okay. Or work is being done by the system or work is being done on the system. So there are these two cases. Okay. So what happens is when there is a change of this, there is going to be a change in the internal energy. That is what we've been covering for the past 4 videos. Okay. So when you have a system whose energy, for example, we're taking it as U. Okay, now when it absorbs a certain amount of heat, the internal energy will increase. And we're talking about it like, so let's say it absorbs Q amount of heat. It is absorbing Q amount of heat. So what is going to happen? The internal energy is going to increase by Q. Not only that, W is the work done on the system. So I'm just going to write work on the system. So the Q is going to be the heat absorbed. So there is going to be an increase in the internal energy by Q, and W is going to be the work done on the system, which means W is also going to lead to an increase in the internal energy. So basically, what's going to happen is, I'm just going to write it again. We are assuming that the initial internal energy equals to U1. Okay, so let's assume the final internal energy equals to U2. Okay, now U2 will be equal to, first of all, the existing internal energy, that's U1, plus the Q which has been absorbed, so plus Q, plus W, which is the work done on the system. Right. So when I shift this to here, U2 minus U1 becomes equals to Q plus W. And so we get delta U equals to Q plus W. Okay, so we are considering a system whose initial internal energy was U1 and the final internal energy was U2. Because the system absorbed some amount of heat in the form of Q, and there was some amount of work which was done on the system as W. So U2, that is the final internal energy, is going to be equal to U1 plus Q plus W. So when we shift it to this side, it's going to get a minus sign, obviously, and delta U will be equal to Q plus W. So basically, the change in the internal energy equals to the heat which is getting added to the system and the work which is being done on the system. Not only that, there could be a case where we have the system where, let's take, for example, the internal energy of the system is done, or rather, let's take a system who has a particular amount of internal energy. Okay, now when there is work which is done by the system, work is being done by the system. So obviously, in this case, we will not take work as a positive, work will be negative because work is done by the system. Not only that, Q is also going to be involved, obviously. So Q is done. Q is the amount of heat which is going to get added, right? So since Q is system is getting, absorbing the heat, Q will stay positive. Okay, Q is going to be positive because this is absorbing. Okay, so similar to this case, delta U, I'm just taking the direct delta U part. So delta U will be equal to Q plus minus W. So Q minus W. And in this case, the change in internal energy is the sum or is equal to the heat added to the system minus the work done by the system. To remember this much easily, what I would say is so when work is done by the system, or when it's done by the system, it's going to be negative. When work is done on the system, W is going to be positive. Heat, when heat is getting absorbed, the Q value will be positive, and when heat is getting released, Q will be negative. Okay, so basically the first law of thermodynamics, the equation is delta U equals to Q plus W, where Q is the internal energy. I'm sorry, delta U is the change in internal energy. Q is the heat that is absorbed or released, and W is work done by the system or on the system. When it's by the system, it's going to be negative. When it's on the system, it's going to be positive. With that, we're done with the first law of thermodynamics. In the next video, we'll be continuing with the next concepts that come forward.